Okay, so hi everyone, welcome to a new week, a new Flan Talk. This week by Xinting, who's going to talk about a formal framework for understanding length generalization in transformers. So yeah, thank you. Please go ahead.
Yeah, thank you, Anay. Okay, so this is a joint work together with Andy, Sedgwick, Yash, Andreas, Haiti, Pritam, and Michael. And yeah, as the title suggests, we study length generalization. And let's start with, oh, wait a second. Okay, yeah, let's start with a simple scenario where we are training a transformer on copy task where the dollar symbol is start of sequence token, and there is an input sequence ABBA and separator. The model needs to output ABBA autoregressively, and finally end of sequence token. And if we train this, and the question is, if we train this transformer on inputs of length less than n, whether if we and we tested on inputs of length 2n, whether the model can still correctly perform the task, assuming that it is trained very well on inputs of less than n. And the answer is, for this task, the answer is no. Here we have training set accuracy of 100%, and we tested on roughly double and triple of the length on out of domain test inputs. And we show that the results are very bad. The model could not length generalize on inputs longer than the training, much longer than the training inputs. And the result, and on the other hand, if we make each symbol unique, in other words, each symbol in the input sequence only appears once, then the model can length generalize very well on this task. Okay, so we have seen that on some tasks, the transformer length generalize very well, and on some tasks, it cannot length generalize. So in this paper, we try to answer this question on which task do transformer length generalize. And there is a previous paper by Zhou et al. Proposing a Rispel conjecture, saying that if a transformer, length generalize on problems with simple programs in Rispel language. And they have done many experiments on different problems and tasks, and show a very strong correlation between whether the problem is expressible by Rispel language and whether the model can length generalize on this task. And yeah, but there is a remaining challenge that the Rispel has not been formalized, and the theoretical understanding of length generalization is still limited. And we cannot also prove that certain problem is not expressible by the Rispel language. So our contribution is that we formalize it based on CRESP, which is another variant proposed by Yang and Jiang. Okay, so to illustrate what is a CRESP program, we can start with this task where there's the input string consists of 1 and 0s, and the model needs to predict what's the most which number occurs most often. So in this case, 1 occurs 6 times, so it should be 1. And we can write a REST program, a CRESP program for this. So yeah, okay. So the first line is that is saying that the count is to count the number of ones. So the Q1 here is saying is a Boolean function, which means whether this current the position J is token 1. And wait a second. Okay. And the second line just counts the number of zeros, and then we just compare the number of 1 and number of zeros, and we can get a CRESP program to solve this binary majority task. And correspondingly, empirically, the transformer can length generalize very well on this task. And on the other hand, we can also write a CRESP program for unique copy, where the first first two line is to see whether the preceding token is an A. So in the first line we count in the previous position whether there is a A. So and if there's an A, then the count is greater than 0, is greater or equal than 0, then then it should be true. And then we collect the bigrams in the previous context. So the first line shows that whether the current position is B and whether the and previous position is A. So and the second line just counts whether there is AB bigram in the previous context. And we say that the next symbol should be A if there is any symbol in the vocabulary such that the current symbol is sigma, and there is a sigma A bigram in the previous context. Then the next symbol should be A. And we can use this program to solve the unique copy task, and correspondingly, the model length generalize very well on this task. And to describe series in more details, we can have in the series we have Boolean value operations and count value operations. For the Boolean value operation, we have this Q sigma, where sigma is one of the symbols in the vocabulary. It's just to check whether this current position is this symbol. And we have propositional logic, and there's also a very important function where the serial periodic local, the periodic refers to this class of phi, and for example, periodic saying that this should be a class of periodic function. For example, the phi can be check if I is congruent to k modulo m, and we can also compare the counts, where the count is obtained by the count value operation, and the main operation here is this one. We just count how many preceding position j satisfying the psi ij and pj. Yeah, and this psi ij can restrict based on position relations. For example, it can be a function like whether j plus 1 equals I. So that means we look at the previous position, and we say, and the series periodic local, and the local refers to this psi. This class of function should be local, and we will explain what is local later if anybody is interested. And yeah, and we also have count arithmetic. And so far, this is all about the series program. And there are some operations from the original series program defined by Yang and Jiang. And there are also some newly added or modified position informations, position aware operations needed to model the absolute position embedding transformer. Okay.
Oh, Xinting, I think there's a question hand raised.
Yeah, a quick question if you don't mind.
Yeah.
Do we have a formal definition of generalizes very well, except, one is green and one is red?
Well, the green one just means that this is expressible in series. So the green and red doesn't refers to whether it is generalized well or not. Yeah, it's more like it is about whether it's expressible in the series language. So actually there's no like a certain criteria to measure like whether it to define like above certain threshold, like it will it means generalized very well. So it's just because we feel like there's no such need to define, because like in the case where our model generalizes good well, it usually generalizes very well, and when it cannot generalize, it's usually very bad.
Okay. Thank you.
Yeah. Yeah, sure. Okay, so for example, for this this kind of periodic function can be used in this to recognize whether the language AA star. For example, we can write the phi can be I modulo I is congruent to 0 modulo 2. So it's checking whether the current position is even or odd. And the serial program for this is very simple. Just count whether there's count the number of non-A character and is 0, and the current position should be even. And for in contrast, for parity, we can prove that there's no serious program. And by the way, the task of parity is to count the number of ones in the input sequence and determine whether it's even or odd. And our proof is and the proof idea is to show that if there is a serious periodic local program for parity, then there is a serious empty set for A star. So the serious empty set means that there shouldn't you cannot use any periodic function here, and the psi here should also be empty. So it's so you can only use a constant t or true here. And we later then show that there's no serious empty program for A star. And also we have we also proved that there's no serious program for copy with repetitions. And this is by communication complexity. We show that if there is a serious program, then there's logarithmic communication complexity. Then, but on the other hand, the copy with repetition need theta n communication complexity. So there's no serious program for this task. And yeah, so far, is there any questions?
Could you tell us more about the logarithmic complexity that you achieve here on the last slide?
Yeah, I have some backup slides for that. Okay, so it's a bit involved. So we just try to say the overall idea. So the communication complexity is to say that assume there is a case where the input string is partitioned into two parts. One is for Alice, another is for Bob. And if we're asking how many bits does Alice need to give Bob, so that the Bob can only access the second half, so that Bob can compute output of the serious program. And we say that the Alice only need to communicate O log n bits to Bob, because the series, as you can see in the previous programs, is largely based on counts. So when in this counting, it aggregates many tokens. Like the attention can be aggregated for all the positions satisfying the condition. So in other words, the Alice can just aggregate them first and then communicate the aggregated value to Bob. And that's roughly the the idea of the proof, even though the proof is kind of very complicated.
Yeah, I kind of get the gist of it. So the CRAS program has you feed Alice and Bob into it, and in a nutshell, it outputs using the order of log n bits to express the output here, right?
Yeah. So
Yeah.
so it's just assuming a case where there's such a scenario where
Yeah. So you will talk we can discuss in detail in the later part of the presentation. Thanks.
yeah, sure. Okay. Where we are. here. Okay. Is there any other questions? Okay, so I can keep going. So the informal version of our theorem is that if F has a series program, then the transformer trained on an idealized training procedure will length generalize from n to 2n when n is large. So we address the length generalization problem as saying whether the model would ultimately length generalize when seeing a long enough training input. And our limitation is that we treat an idealized training procedure instead of S3D training, but our experiments show a very strong agreement with the theory's prediction. And before we go into the proof idea, we need to introduce some settings. So we study the absolute position embedding, and each position embedding is learnable. It's like GPT-2 architecture, and at training time, each input is encoded with some kind of random offset. So instead of, so because we need to test the model on longer inputs and training on shorter inputs, so the maximum context window during the training is longer than the input string. So instead of just assigning each token with position embedding P1, P2, starting from P1, we start from a random offset, say PO plus 1, PO plus 2. In this case, we can make sure that all the position embeddings are trained. Instead of, otherwise they won't be, otherwise during testing, there will be some untrained position embeddings. And we say that this is a valid design because it mimics how it works in LLMs. Because during training, in real-world training, these language models are usually get a very long input, which is a concatenation of different text and of multiple text, and a certain task or a certain input string can occur at any position in the context window. And we say that the absolute position shouldn't matter. And another important assumption necessary for our proof is that we say the transformer algorithm should be invariant to the offset. This is saying that the model shouldn't do different things at different if the input string is aligned with different position embeddings. So so the idea is, so how do we formalize this? So for the first idea is that we have, we can, in order to make the model not sensitive for the position embedding, we can just have position embeddings equal to each position embedding with an offset, but this would make all positions indistinguishable. And so we have a better idea is to make attention patterns invariable to offset. So we have a lot of these terms. So so in the transformer, in the residual stream, we have the residual stream can be decomposed into a sum of many terms. For example, the position embedding, token embedding, and output of previous attention layer and of the MLP layer. So each residual stream is a sum of all these terms. And so when computing the keys and queries, we can have, so we have this sum multiplied by the key and then another sum multiplied by the query. And if we expand this, this product, we can have individual terms for each individual term in the residual stream, like the position embedding and the position embedding interaction. And yeah, this is part of the computing or computation of attention logic before the softmax, where we're saying that we assume that this should be translation invariant or offset invariant. So when we add the same delta to the pi and 2pj to the pi and pj, the product should be the same. And because we have a lot of and there is not only the direct connection or direct interaction between the via the query and keys. We can also have position embedding multiplied with other values in the previous attention head, then multiplied with the current query and keys. So we have many of these kind of terms. And we also assume that this should be offset invariant, and etc. And similarly, we make sure we make the MLP output offset invariant. And formally speaking, it's just look like this. We have many intermediate matrices M1 to MK, and this should be, and the contribution from the contribution to the attention logits from the position information should be offset invariant, like this. Like you have almost constant value along the diagonal or subdiagonal. Any question so far? Okay, so I can keep going. So there is, So this is an important assumption, but we have real-world evidence supporting this assumption. So for example, for the transformers we have trained in this paper with SGD, we examined the transformer, like we examined these products, we show that this pattern is very strong. And also we checked GPT-2 small, and also approximately exhibit this pattern, this translation variance. And it is an interesting open problem to prove its emergence from SGD dynamics. Okay, so we then also need to introduce the inference procedure, which is not normal SGD training. It is saying, so for f be the target function, then for all the input length, we have transformer Tn. It should have context window n, and it matches f only on input length up to n/2. So this mimics the training on the shorter length, but the model can be tested on longer length. So, and also it should minimize a regularizer. This regularizer would include a lot of terms. It includes the number of layers, number of heads, and the precisions, and the various rank and norm of the matrices. And lastly, it also includes the term that punishes the interaction between position embeddings directly via the query and key matrices. And any question so far?
Can you just say in one sentence what is a regularizer?
Yeah, it's I think that try to keep something bounded.
Okay.
So for example, here we bound, for example, the number of layers and heads. We try to find as smaller like number of layers and number of heads as possible, but we don't but this regularizer does not include the number of the model dimension in the paper we call it width. So it does not, it allows model to use larger and larger dimension as the input length increases. And because this is needed to distinguish more and more positions. Yeah, so we try to find some for example, we try to find a model with small number of layers, and doesn't do very weird things.
Thank
you. Yeah. And so let's come back to our theorem. So we assume that f is definable in CRESP. Then there is some, and having our inference procedure, then there is some unsuch that for for the small n, for all the lengths greater than this big N, the transformer trained on this the transformer on this length would match the F on all strings up to length N, because the transformer is trained on length up to N/2. So this is basically saying that this would length generalize. I see some message in the chat. Right there is there.
I think you can go on. It's
Okay.
then explaining stuff.
Okay. Yeah. 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 So the proof idea is saying, so for example, now we have a serious program, and our inference procedure will give us many transformers as we increase the length of the yeah, for each N we have we train the transformer, and this transformer and this inference procedure will traverse as many distinct transformers. You will train the transformer H length, and because our inference procedure would choose a small regularizer, and because the existence of serious program, this true condition would entails that the regularizer RTN stay bounded. It does not, like, as the N goes to, as the input length goes to infinity, the regularizer doesn't diverge to infinity. And because the bounded, and because the RTN is bounded, and it allows us to compress all TNs into only a bounded number of distinct algorithms. Or in this paper, we formalize it as limit transformers. So yeah, in other words, during the inference procedure, we can have infinitely many distinct transformers, but we only have finitely many distinct algorithms. So the number of algorithms is bounded, while it's like there are many transformers. So each algorithm can correspond to multiple transformers. And because there are infinitely many transformers, so some algorithm would correspond to infinitely many transformers. And yeah. And each of these algorithms will either be ruled out at certain lengths or keep reappearing. So because during the training procedure, each Tn only partially match the function, because we train it on length up to 2 over N/2. So and this algorithm match the behavior of each algorithm match the behavior of each transformer. So the algorithm we can only make sure during the training procedure that this algorithm partially match the function f. So if algorithm only partially match the f up to a certain length, so that means if we increase the length, increase the n to make it larger than this length, then this algorithm is not will be rolled out at this length. So in other words, some the algorithms would if the algorithm only partially match the f, then it will be rolled out at certain length. So if we keep increasing the length in the inference procedure, then we will have we will roll out more and more algorithms, and only the correct one will keep reappearing. And once that happens, we can say, once that happens, that means because another thing is that because the number of algorithms is bounded, so we can have so we can ultimately roll out all the incorrect ones. And yeah, once we reach that point, there's only all the trained transformers would correspond to the correct algorithm, and this algorithm compute f at all lengths. So the corresponding transformer would compute f of up to n, which means it will length generalize. Yeah. Any questions at this point? Okay, so I just keep going. Yeah, so on one hand, we can prove that if f has a series program, then it is length generalizable. And on the other hand, we can prove certain problem cannot be expressed by series, which means yeah, in our results, we cannot directly say that you cannot length generalize. We say that yeah, if certain problem it cannot be expressed by limit transformers, you cannot length generalize. So yeah, so a series is kind of a subset of the expressivity of limit transformer. Anyway, so we need to prove certain problem cannot be expressed by series. And we do this by this logarithmic communication complexity, which I have mentioned before. And we do this, and we use it to prove that the copy and addition and DAC2 is not in the set of series periodic and local. And for other, like to prove this inexpressiveness, we use a mixture of techniques, and other techniques can include reduction to already known results that the series cannot express parity and the series cannot express ABE star AE star. And yeah, so so many of these proofs are proven directly, and some of them use the already known fact about majority logic. And note that many inexpressivity of languages can follow these results because we can reduce them into the already known results. Okay, so let's come to the experimental results part. Yeah. Okay, so for the binary majority task, we have shown that there is a series program for that. And the experimental results just saying that if we train it on lengths from 0 to 50 and test it on double and triple of the length, then the model can still achieve 100% accuracy. And yeah, there is another binary majority interleave task, which means that we interleave 3 binary majority inputs. That means for the position 1, 4, and 7, and so on, they belong to one binary majority input. And for position 2, 5, and 8, and so on, they belong to another binary majority input. So the model needs this kind of periodic attention pattern to solve this task. I would say that this is the solid line corresponds to the transformer with absolute position embedding, and the dotted line corresponds to the transformer with no position embedding. I would say that the no position embedding can be understood. The length generalization on no can be understood by the series empty set. So the green saying that it's in series, and red saying that it's not in series. Yeah, the green here showing that it's in series periodic and local, and the red saying it's not in series empty set. So roughly speaking, the red means that our theory predict it cannot length generalize, and the red and the green means that our theory predict it can generalize. And for the next task, it's yeah, kind of blocked by for the majority task, it's we can see that our theory matched the empirical results very well. We predict it can length generalize, and it indeed length generalize. And we can have sort, it also matches well. Note that the bin 2 is also out of domain, longer inputs. And here for the unique copy, we have the green is also the green line is also flat, and the red line also rapidly decreasing. And for copy repeat, copy with repetition, we also show that yeah, the theory also matches the empirical results, and this is also true for parity, and this is also true for addition. So in other words, for all these algorithmic tasks, our theory predicts the empirical results very well. So, and we also have tested our theory on a battery of 17 regular languages from Padamishra. So there have yeah, we don't do any cherry picking. We just use the whole collection of these languages, and we write we show that whether they are whether they are in or not in serious language serial program. And yeah, there's one group of people doing this, another group of people doing a very empirical experiments, try to test whether each of the transformers, whether the transformer can length generalize on each task. And when the two groups of people are done, we found that the results match very well. We can see that all the green lines are flat, and all the red ones are just decreasing very rapidly once the training lines, once the length is longer than the training length. Yeah, and also we say that the established classes like circuit complexity, like dotted depth, don't predict or don't match the empirical result very well. And yeah. So in summary, we have we answer the question on which task do transformers length generalize. We have built a theory saying that if F has a serious program, then transformers trained on an idealized training procedure will length generalize from n to 2n when n is large. And the empirical results strongly supports this theory. Yeah, and there's also some open questions like currently like the rope is more popular, and we expect the theory but our theory applies to absolute position embedding and nope in this paper, but we expect the theory likely can carry over with similar power with ape. And also the results is for also it's open question that how to prove the results for the gradient-based learning and finite subsampling of training data. We also think that is an interesting direction to do. Okay, thank you.
Okay, thanks for the talk. So as always, we'll stop the recording now.